So Josh started this work on PMTs. He did the initial Flatbuffer work. And then I came in and complained about old GNURadio code. And he said, you can take over. We're going to talk about, I know that many of you are probably very familiar with PMTs. Others of you have no idea what I'm talking about. So I'm going to go over some definitions and some overview of the terms with PMTs, data serialization, and modern C++. And then once we have that foundation, we'll move on to talk about the new PMT classes and then where we're going. So what is a PMT? It's a polymorphic type. Great acronym. It's used to group arbitrary data types together. In C++, everything is strongly typed. So if you were to declare, say, a standard template library map, all of the data in there has to have the same data type. But frequently, we need to be able to support different data types, and that's where the PMT comes in. It's like a Python dictionary or JSON, but it's in C++. It also includes handy serialization and deserialization functions, so we can send data between processes or over the network. So I alluded to this a little bit, but why do we use PMTs in GNURadio? There's two primary uses that I'm aware of. The first is we want to tag samples in the data stream. A really good example of this, many of you are probably familiar with, is when you're using a usurp, you'll get an rxtime tag. This is I believe it's a tuple that includes integer seconds, unsigned integer seconds, integer seconds as an unsigned 64-bit integer, and fractional seconds as a double. So that'll get tagged to a specific sample in the data, and then when you're processing, you can say sample X was exactly at this time. We also frequently send data between blocks and asynchronous messages. So I came up with my super terrible burst detection message. You would probably want other fields in your burst detection message, but just to kind of give you a flavor that maybe we'd put the modulation type in there as a string, we'd put in the bandwidth as a double, and then there could be a one-up counter that we're using for the burst ID. So in GNURadio, moral of the story is we need to be able to store these disparate types to describe the metadata for our signals. So if we already have PMTs, why are we looking to do something new? So if you're asking that question, maybe you haven't used PMTs enough, but the interface is kind of consistent. It can be hard to understand. One of my favorite examples is if you want to create a PMT from a signed integer, the function you use to do that is from long. Later, you'd like to check and see if that PMT came from a signed integer, but you don't use isLong, you use isInteger. And so some of these inconsistencies just add a little friction to using PMTs. Some of the operations that are pretty common can feel a little clunky, and they can be hard to, the names and the arguments they take can be hard to remember. The little code snippet here maybe is a little harder to read than what I had hoped, but the example I have here is trying to get if a key is present in a PMT dictionary, extract the value out. And so I have the first function I call is to see, is the key present? Then I get a reference to the key from the dictionary, and then finally I extract the value out, which in this case is my sample rate, from the dictionary, and then able to go on my way. Feels like a lot of work. In many cases, for what we're doing, you have one or two tags or very small messages you're transmitting. Performance isn't a big deal, but there are people who are trying to do a lot more with PMTs, and there can be some performance hangups. And then lastly, PMTs are a custom idea. It's only used in GNURadio, and there are a lot of other people who are looking to do similar things or have been doing similar things. And so the hope is that we can leverage work that other people have done and make PMTs better and easier for everyone. So serialization. In its I guess in its basic form, we want to get data between different locations, and we need to put it into an invertible representation and then get it back out. So PMTs already provide this, but there's lots of other options. There's literally dozens of options. I picked 3 that a lot of people are familiar with and that were considered as we were looking at making this change. So JSON is well known and mostly loved by developers. You store data as strings, very easy to read and write, but it's really slow because you're converting things back and forth between strings. Protobufs is a protocol that is maintained by Google, and it stores everything in predefined structures. And it's got a very ingenious packing scheme where you're able to transmit the data very efficiently over the wire, but there's some computational overhead associated with that. Flatbuffers is also maintained by Google, but it takes kind of the opposite approach, where you're going to have still predefined data structures, but they're going to be transmitted in a less space-efficient way, but with better performance. So if you read the title slide of the talk, you know that we picked Flatbuffers. So let's talk a little more about Flatbuffers and what they are, what they buy us. So it's a memory and computationally efficient serialization format, structure serialization format. Like I said, it's open source, maintained by Google. The data is stored in its serialized format, so there's no overhead to moving the data back and forth. It's already in the format that you want for that. You also, because it's stored in a flat structure, can access any element without having to know the values of the other elements. JSON and protobuf, you have to deserialize other values to be able to get at the value that you want to get at. So it's kind of like just using a struct in C++. Flatbuffers has support for C++, Python, and most any other language that you would want to use. And as I've been describing this to people, one of the first questions they have is, well, I really like a PMT map where I can put arbitrary data in. Are you going to throw that away and make me use predefined structures? So Flatbuffers has you covered there as well. So you can define optional and repeated fields, and that allows us to provide the same sort of interface that you guys are used to with PMTs, where you can define your arbitrary data structures, or you could define a well-defined structure as well. And the next really cool thing that Flatbuffers offers us is what they call structure evolution. So imagine a case where you have a C++ structure that, say, defines your really fancy burst detection message. You're using this, you've distributed it to a wide variety of parties, and then you realize, oh, I probably need some timing information in there. So in this case, I want to add in a duration field. Yet again, still a terrible burst detection message, but I'm adding this field and making it slightly better. Now you need to go to every single party and say, okay, recompile all of your code, grab the new header, recompile all your code, possibly change function signatures, whatever you're dealing with. With Flatbuffers, it's designed so you can add or deprecate fields without having to inform parties that don't depend on those fields. And so someone that wants that duration field still needs to grab the new header and recompile, but a party that doesn't care about it can use their old code without any changes or recompilation. This will lead to one of the features that we'll talk about in a few minutes. So how to use Flatbuffers? They sound kind of like magic. They're a little bit like magic, but there's a process you have to go through. So you're going to write a Flatbuffers schema file, which is going to have a structure that looks kind of like a C++ header file, but it's a little different. You can think of it kind of like a JSON schema where you're defining names and data types. And they have a really good guide that's available, which is pretty much all of the information you need to know to specify one because it's a really simple specification. So once you have that file, you're going to compile the schema using the FlatC compiler. That's their fancy compiler that will produce, in our particular case, a C++ header file. But because it supports a variety of languages, you could also produce bindings for Python, Go, whatever language you want. You take the header file it produces, you include it in your code, and you're ready to start working with that flat buffer. So it's a fairly easy process to get going. Okay, this is the last introduction kind of definitional slide, and then we'll get into the fun stuff. So we're going to be using modern C++ here. So I Googled, what is modern C++? And there's a lot of terrible definitions for it. So what most people say is you're using anything that's been introduced since the C++ 11 standard. The way I like to think of it is you're trying to make C++ look more like Python. And why wouldn't you want to? So some of the really common concepts that you're going to see in code that describes itself as modern C++ is it's going to use range-based for loops, which look like Python for loops. It's going to extensively use templates to make it so you can call functions with a wide variety of types, kind of like Python duck typing. And you're going to declare complex variables types using the auto keyword, kind of like in Python how you don't have to know the type to get a return value from a function. So I put up a pretty simple example here. You've got a Python dictionary for loop where I'm just printing out the values, the key in the value in there, and I've got the equivalent for loop in C++ using these features. And it's not quite as simple as the Python, but I think it's pretty slick how close it is. So with all of this, we're ready to talk about the new PMT classes. So it's been moved into a standalone project, so it could be used outside of GNURadio. And it also doesn't depend on any code in GNURadio, so it's nice to have that modularity there. And if you'd like to contribute to it, I'm happy to accept any help. So we created these new PMT classes, and they're all based on Flatbuffers. And because Flatbuffers already do most of what we want, these new classes are really just a thin wrapper around them that provide some normal functionality, make it look and feel like you're using standard template library containers that you're probably already familiar with. So let's go over several of the types that we've defined and some of the types that we're going to define. So the first and simplest type is a PMT scalar. This is wrapping a single value in a flat buffer. It's used for signed, unsigned integers, floating point, complex numbers, and the API is designed to make it really simple and easy to use. You can construct it from whatever value you want. One thing that took a little bit of effort, but I think is really nice, is in a lot of cases you can use it as though it were not a PMT. And so I've got in the middle there where you're checking that the PMT value is equal to a floating point value, and it doesn't matter that it's a PMT, it still interacts properly with the floating point value. And you can get the value out really easily as well, just by casting it back to the floating point value there. The next type is a PMT vector. So this is a contiguous array of data of the same type. So the current PMT equivalent would be a uniform vector. The goal here is for this to feel like you're using a standard template library vector. And so the API matches the STL vector as closely as possible. So in the code snippet here, which I apologize if it's hard to read, but you can construct it using all of the constructors for an STL vector. In this case, I'm producing one from a complex float. You can use range-based for loops. You can index it using the bracket operator. The goal, yet again, is that it feels just like you're using a standard template library vector and that it doesn't feel like you're using some bespoke object. The next one is a PMT map. So this is a collection of key value pairs, like a dictionary in Python. For now, all of the keys have to be strings. I have a goal to relax that in the future so that you could have any PMT be in there, but there's some effort that needs to go into that. And the value can be any PMT, scalars, vectors, other maps. And for insertion, here I've got in the middle where you don't have to already put something into a PMT to get it into the map. You can take, in this case, the map PMT important is equal to a scalar 4.0. It will automatically convert that to the right kind of PMT and put it into the map. You can also put PMTs in there. You can use range-based for loops. And again, the goal is that this feels just like you're using a standard template library map, but you can put any type of data that we can store in a PMT in there. So these are the three types that we have working today. In the future, we want to add in some new types, and the library's been designed using templates so that it is really easy to add in new types, and you don't have to change any of the existing types and say, oh, I need to add knowledge of this over here. It should be pretty modular and transparent when you're adding something new in. We want to have a string type, should be fairly straightforward, and match a standard template library string. We also want to have a vector that matches the current PMT vector, which would mean that all of the elements are PMTs rather than uniform data. These are going to give us the primary data structures that the vast majority of the cases I've at least seen are using. There's no plan right now. There's a lot of different data types that the PMT supports. You can have a vector, a list, a tuple, a pair. They're all kind of similar, but if you use the wrong one, it's going to give you a wrong type error. And the goal is to keep it kind of simple with the number of types that we support and not have every single type available. However, if there is a need for it, because it's designed to be modular, it shouldn't be that difficult to add in those types in the future. The thing that I'm really excited about is adding in the ability to specify a formatted type. So PMTs, they store arbitrary data. If you've got a PMT dictionary, it's going to have some set of keys and some set of values. But when I'm writing a block, I want specific keys with specific types of values. And so going back to the example from earlier, if I need to read the time tag from a data stream, I want to know that I have a unsigned 64-bit integer and a double value that represent what I want. Right now, there's no way to specify that that's what you want, and you need to do the data validation yourself. So Flatbuffers can provide a lot of that data validation for free. A Flatbuffer is already a packed data structure, and you can go from a Flatbuffer to a struct, a C++ struct, and back and forth. And so you can get the type checking for free. That doesn't necessarily solve you. So data validation is a really hard problem. And in general, you can't just have a JSON schema even and say, oh, I just throw that at that and I know my data is good. And so I'm not guaranteeing that every case this is going to solve all your problems. But in a lot of cases, just knowing that your data is of the right type is a huge win. So new PMTs, better interface, sounds great. But if it's slower, nobody cares. And so we've done very limited benchmarks. And by very limited, I mean 2. And so I do not promise that this is the full extent of the performance of it. There's definitely a lot more we're going to do, but we wanted to provide some numbers to show you guys today. And the tests that were done on vectors and maps, at least in my experience, those are the most common types that are used. And so right here, I've got a chart that shows you vector serialization. So the old vector serialization is in blue, and the new version is in orange. So what you can see is we still have a little work to do. The That's about 18,000 elements, which is a really big vector. Prior to that, the new code is faster than the old code, which is great. But after that, it's not as great. So I went through a few days ago and found in the code where we've got an extra copy. And that's one of the first things on my to-do list is to fix that. And that should bring the performance so that it is at least as good for the new code as it was for the other code for all data sizes. But to begin with, it is better for up to about 18,000 elements. For the map, this is where things get interesting. So, I guess I should mention on this one and the previous one, the y-axis is time, so smaller is better. So this graph looks weird. I'm going to explain it a little bit. So the flat lines at the bottom are the new code, and the sloped lines are the current code, and we're looking at element access within a map. So what this tells me looking at these sloped lines is that the current map is implemented as a linked list. And so when you're trying to access a key inside the PMT, it has to scan through the whole thing, and on average, it's going to scan through half of that before it actually gets there, which means it's really slow to access in there. The new PMT is implemented as a map using the standard template library, which I believe is using a red-black tree. But it's fast, it's got your logarithmic complexity for accessing an element, and so it's not quite as good as what it looks. It does actually take time to access the elements in there, but it's a lot more efficient, which if you have a lot of data, metadata that you're storing, means you're going to get better performance using it. So where are we going from here? The code is not quite ready for prime time. It's getting there, and I hope to be there in the next few months. At that point, we'll want to get it integrated into GNURadio, whether it makes it into 3.10 or the 4.0 or 3.11. Depends on when exactly those things line up. We want to add in the PMT types that we talked about from the previous slides, and we want to make it easy to work with PMTs outside of GNURadio. This is something that I think is really cool. So the Flatbuffers libraries exist for most every language. And one approach to having PMT support would be to write a wrapper library for each of these languages. I don't want to maintain that. I don't know how to write in Go or, I mean, I could, but I don't want to learn how to write in all those languages. So we could make GNURadio be kind of a universal acceptor for Flatbuffers messages, and then Google is writing our support libraries for all of the other languages, and we are just accepting these messages. So I wrote a super fancy example. So imagine that I've got a JavaScript-based web service. It accepts some user input and then produces a message that goes to our application. So when the user clicks send, the JavaScript web service is going to use the Flatbuffers library for JavaScript, and it's going to produce a Flatbuffers message. We'll have a receiver block, which could be implemented as a message broker or through a message broker or as a server. It receives that message. It then converts that to a PMT and sends it to the rest of the flow graph. What's great about this is I don't have to explain to the JavaScript designer what a PMT is, what GNURadio is. I just give them the schema file, which is compiled into what my header for C++ and their bindings for JavaScript, and we both go on our merry way. So that's what I've got for you today. If you have any questions, please ask. And yet again, if you want to contribute, this is in the GNURadio GitHub page as its own PMT project. Are there any questions?
All right, do we have any questions here? All right, Jacob.
Would you plan to package this separately from GNURadio to make it more accessible?
Yes.
Okay, and I think that's a great idea.
So the current PDU in GNURadio is explicitly a pair of like a map and a vector.
but you said you weren't thinking of including pairs in the Flatbuffer implementation. What would be your replacement for a PDU?
So you could do a dictionary where one of the keys was, say, data, or you come up with a better label for that, but that would contain the vector that had all of your data in it.
Just a comment, I would just create an explicit PDU type while you're doing a structure type that is a PDU to avoid, any confusion as PMTs have had with what, is this a PDU or not?
Oh, okay, thank you guys.
All right. Well, thanks so much, John. And I assume you'll be available on the chat some if there's further questions.
Yes, I'll check the chat, and I'll also be at the conference, so you can come find me or chat me up if you'd like.
All right. Cool. All right. Thank you.